Hey everyone, so this one is going to be a segment on section 7.6 of chapter 7. So picking back up to where we left off before, enthalpy. So we haven't talked about enthalpy yet. Uh, this one is definitely an important topic in thermochemistry. Just to give a little bit of a refresher of what we talked about earlier and how it's related to what we're going to talk about now. We talked about how energy evolves as heat when you're keeping your container sealed at a constant volume, right? So that's the first bullet point here. It says when a chemical reaction occurs in a sealed container under conditions of constant volume, the energy evolves as heat. Right, we've seen that the delta E, the change in internal energy, is equal to Q plus W. But when you have a constant volume, the W becomes zero, the work becomes zero, and you're basically left with just Q. If W is zero, then delta, the change in internal energy, is just going to be Q at constant volume. But what if you're at constant pressure? That's something we didn't talk about yet. And that's related to this concept called enthalpy. So when you're at constant pressure, right, the heat evolved in a chemical reaction at constant pressure is what enthalpy is. Now, what do we mean by constant pressure? We basically mean that the reaction's open to the atmosphere. The pressure isn't changing when you're running a reaction open to air, open to the atmosphere. Right? The pressure in the atmosphere is pretty much constant, and it's barely changing. It's negligibly changing when there's a chemical reaction going on. Right? So how do we quantify the amount of energy that results at constant pressure? Realize that the energy can evolve as both heat and work at constant pressure, right? So delta E equals Q plus W, and we know that at constant volume it's just Q. But when we're talking about a chemical reaction that occurs under constant pressure, we can have both heat and work. But the thing is, we are not really interested in the work that's done. In most cases, right? It says in many cases we're not interested in the work done. We are only interested in the heat exchanged. So why do we keep disregarding work? Like, what's the issue with work? Why can't we just calculate work, right? It's not like it was that hard to do when we were in the previous videos when we were calculating work. Work is just equal to negative P external, right? The external pressure times the change in volume. So what's the issue with calculating work? It's not that there's really an issue with calculating work. It's that it's not really necessary, right? Because we don't care about the work that's being done in a chemical reaction. As chemists, we care about how much heat's being produced, right? It's kind of like having this analogy. Imagine I'm cooking food. And in chemistry, there's a lot of quote-unquote cooking involved, right? You're mixing several chemicals and you're trying to make some sort of product, right? So there's a couple things in chemistry we care about. One, we care about the products that we make, right? And the other thing we care about is how much heat is evolved in the process or absorbed. We're not so concerned about the work, right? Like if I'm cooking food on a stove, I'm not really worried about how much work is being done by the stove to cook my food, right? I just care that the stove is supplying heat in the, energy in the form of heat to cook my food, right? So the work being done isn't really something that we're trying to quantify here. If we could omit the work out, and that makes life easier, right? If we only have to calculate energy in terms of Q, and we can take out W just like we did before with calculating delta E, we could try to do that at constant pressure. So at constant pressure, we have this quantity called enthalpy, and let's dive more into that and what that means in terms of context of thermodynamics and measuring energy at constant pressure. So enthalpy is given H. Okay, that's the so internal energy we said is E, right? So enthalpy is H. That's the notation we use. We define enthalpy of a system, H of a system, as the sum of its internal energy E, right over there. H is equal to the internal energy E, and the product of its pressure and volume, P and V. Okay, that's just how it's defined. Right, we're not going to get into the specifics of where this equation actually came from. We just know that enthalpy is equal to the internal energy of a system, E, plus the product of pressure and volume. Okay. Now, because internal energy is a state function, we talked about how that's a state function. Pressure and volume are also state functions, right? So if a pressure or volume are changing, we're not always talking about how the pressure and the volume change, like what influenced it to change. We just know that if we start at a certain volume and we end at a certain volume, or if we start at a certain pressure and we end at a certain pressure, we can think of those as state functions, right? Where we care more about the state, not how it got to a particular state. So if they're all state functions, we can basically communicate this equation in a little bit of a different way. We can say that the delta H, now instead of H, we can say the change in enthalpy, the change in H, delta H, is equal to the change in internal energy plus P times the change in volume. Now, if all of these are state functions and we can describe every state function as a change from final to initial, why are we not putting a delta in front of P? Why are we not saying change of P? Well, because remember, enthalpy is under constant pressure. So if it's under constant pressure, we don't put a delta sign there, okay? So it's delta H equals delta E plus the product of pressure times the change in volume, okay? But to better understand this expression, let's kind of express all of these terms on the right with stuff that we already talked about before. So here's this equation again, and notice I used some color coding for it. So I just basically took this equation and I put it over here, okay? And notice I have the internal energy E in blue and the product of pressure and the change in volume in red. Why am I using this color coding? You're going to see in just a second. Realize that we can express the change in internal energy delta E as Q plus W. We've seen that already 1,000 times, right? And if we're at constant pressure, we're going to describe the heat as Q at constant pressure P, right? So subscript P. So now it's just Q at heat at constant pressure plus W. That's going to be delta E, right? Now, in addition, if we're trying to express, the change in enthalpy or the change of internal energy in terms of pressure volume work, like we looked at in the previous videos, we know that the W work is equal to negative of an external pressure, right? Because we're pushing against an external pressure, times the change in volume, okay? And I can rearrange this equation to basically say that, if I multiply the negative on both sides of this equation, I get negative W equals, now if you take a negative multiplied by a negative, it becomes positive. Negative W is equal to the external pressure times the change in volume. Now, why did I do that? Why did I multiply the negative on both sides to express it this way? Well, because if you look at the enthalpy equation, the pressure times the change in volume is positive, not negative. And that's what I did over here. I expressed the pressure, the product of pressure and constant volume as positive. And what we're going to do is we're going to plug in these into our equation. So now we can express delta H equals delta E plus P delta V and plug in E for QP plus W, right? Because that's what that equals, plus negative W, which is right over here, okay? I know there's no EXT here, right? But we don't have to worry about the EXT. That just means external pressure. The external pressure part of this equation is already implied. So we're allowed to plug in negative W for P times the change in V. And what you'll notice is that when you put this together, it's QP plus W plus negative W. And the W's just cancel, right? W minus W is 0. So bottom line is, that's how we're taking work out of the equation, right? Now we have delta H equals the heat at constant pressure, okay? So that all we did was just manipulate the equation to get the change in enthalpy is equal to the heat either released or absorbed by a chemical reaction at constant pressure. Okay, the key thing is constant pressure. Now, what's the difference between delta H and delta E? Because we talked about delta E in previous videos. We're now introducing this new concept, delta H, the change in enthalpy. What's the difference between the change in enthalpy, delta H, and the change in internal energy, delta E? What's the difference? Well, conceptually, they're actually, and even numerically, they're pretty similar. Because they're both state functions, right? And they're basically representing changes in a state function for a particular system, like a chemical reaction, right? But delta E is a measure of all the energy, heat and work exchanged with the surroundings, right? And we know we can calculate delta E by just paying attention to heat and not work. We saw that with bomb calorimetry, right? But we know that delta E is equal to Q plus W, so that's a measure of all the energy, heat and work exchanged with the surroundings. Delta H, on the other hand, is a measure of only the heat exchanged under the conditions of constant pressure. So we're not even worried about the work. Like we said, with enthalpy, we don't care how much work is performed on the system or by the system. We don't care, right? We just care about the heat exchange because we're at constant pressure and we're really just worried about heat exchange. For chemical reactions that do not exchange much work with the surroundings, that is, those that do not cause a large change in reaction volume as they occur, delta H and delta E are nearly identical in value. That makes sense, right? Because if you're not doing much work with the surroundings, think about it. Like when you're cooking food on a stove, and let's say you're cooking your food on a pan, right? The pan isn't sealed. I mean, you could seal it if you want, but let's just say that the pan is open to the atmosphere. You're cooking your food, and all the steam that's produced from the food, all the, that's just all evaporating. It's all open to the atmosphere, right? There's really no change in volume, right? When you're cooking food, you're not changing the volume of the system, right? Everything's open to the air. So how could there be really a change in volume? Which means there's not much work being done. Everything is basically in the form of heat, right? Q. So that's what we mean when we say for chemical reactions that don't exchange much work with the surroundings, right? There's no volume expansion, with something like this, and they don't cause a large change in volume. So delta H and delta E are going to be pretty much the same if there's no work being done, right? But for chemical reactions that produce or consume large amounts of gas and result in large volume changes, delta H and delta E are going to be different in value, right? Because one considers work and one doesn't. Which one considers work? Remember, delta E considers work and heat. Delta H only considers heat, right? So in cases where there is a substantial change in volume, delta H and delta E are going to be different somehow because now you're accounting for a volume change and therefore work that's going to result from that volume change. All right, what about the signs of delta H and delta E? So the signs of these basically follow the same conventions, okay? So we've seen in previous slides that delta E, the sign of delta E is positive when the system is absorbing thermal energy, right? So if it's getting thermal energy from the surroundings, the delta E is going to be positive, right? If the system is losing internal energy, delta E is negative, right? So I want to recap that again. I want to say, so for delta E, positive if energy's going in to the system, right? And negative if energy is coming out of the system, right? Same thing with delta H, very similar. A chemical reaction with a positive delta H indicates that heat, remember, not work, because delta H doesn't, we don't care about work for delta H, we just care about heat, right? Delta E is heat and work. Delta H is just heat. But positive delta H indicates that heat flows into the system from the surroundings. So it's absorbed from the surroundings. We call this an endothermic reaction. Okay? So bottom line is a positive delta H is endothermic. Endo means like, into. An example of this in, you've seen this before, definitely, is when you take a cold pack. What you're doing is you crack the cold pack, right? And then what happens when you do that is you got the chemicals mixing in the cold pack, and the chemicals in the cold pack are needing heat from the surroundings into the system. So imagine the cold pack is the system, and everything that the cold pack is surrounding is the surroundings, right? Like your arm. Let's say you're putting a cold pack on your arm. Your arm would be the surroundings in addition to the air that's around the cold pack. But bottom line is the cold pack is taking heat from your hand, and your hand or your arm is the surroundings, and the heat is flowing into the system, right? Into the cold pack. And that heat is absorbed from your arm to the system, which is the cold pack. Now, a chemical reaction with a negative delta H indicates that heat is flowing out of the system to the surroundings, and that's called an exothermic reaction, right? Exo meaning out. Easy example of that is, you have a stove, and you turn on the burner, and heat is being expelled to the surroundings, right? To the surrounding air, and the system would just be the stove itself. Right? So again, heat is flowing out of the system, which is the stove, to the surroundings, making the surroundings hotter. Okay? All right. So that's basically the difference between endothermic and exothermic. All right. Let's do some practice problems related to this. So identify each process as endothermic or exothermic and indicate the sign of delta H. So let's look at the first example. Sweat evaporating from skin. Would that be endothermic or exothermic? Let's think about that. Well, sweat evaporating from your skin is going to cool your skin, right? So think about it. The sweat had to absorb heat from your skin to evaporate. Right? It's not going to evaporate otherwise if it doesn't do that. So if it's absorbing heat from the surroundings and it's going into the system, that's endothermic. All right, let's just check our definition again. Endothermic. Heat flows into the system, absorbed from the surroundings, right? The surroundings is your skin. So your skin is the surroundings, and the sweat is the system. So what's helpful in solving these kinds of conceptual problems is defining the system and the surroundings, right? If the sweat is evaporating from the skin, the system had to absorb heat from the skin, from the surroundings, to make this happen. So this is why it's endothermic. Okay. What about water freezing in a freezer? Okay, so let's think about that. The water is the system, and the freezer is the surroundings. So when water's freezing in a freezer, it's releasing heat, right? And is therefore endothermic, right? A refrigerator system, the freezer has to remove heat for the water to continue to freeze. Okay? So if the system is releasing heat to the surroundings, that's going to cause water to freeze, right? Think about it. If let's go the other way around. If water was, let's say, boiling, right? If water is boiling, that means it has to take energy from the surroundings to the system, which is the water, to get it to boil, right? The only way water is going to boil is if it absorbs energy, right, from the surroundings to get it to boil. But freezing is the other way around, right? Freezing, it's releasing energy to the surroundings, not absorbing, releasing. I know sometimes that could be a tough concept to wrap around, but water, in this case, is releasing energy to the surroundings, and the refrigeration system is constantly removing the heat that the water released to the surroundings to keep the water cold. All right, so this is going to be exothermic. All right, wood burning in a fire. So you could think about that. If wood's burning in a fire, wood's the system, fire's the surroundings. So the wood is absorbing the heat from the fire, which is the surroundings, right? If it's absorbing heat from the fire to burn, that's going to be exothermic. Right, because the system is now going to release heat. Right, the system being the wood. Okay, so just a couple of examples to get this wrapped around your head. It takes a little bit of practice to kind of digest what's going on there, but like I said, if you define the system and the surroundings, you should be okay. All right, now here's some more practice problems. So this is going to be in your problem set. Identify each process as endothermic or exothermic and indicate the sign of delta H. I don't think we did that before. Did we indicate the sign? Endothermic is going to be positive. Exothermic is going to be negative. Bottom line is, whenever you see anything that's burning, you can associate that as exothermic, right? Okay, so I want you guys to do this one on your own. Try these out on your own, and I'll post the answer key for these. I'll write out the logic of the answers as well, in case you're wondering why something's considered exo or endothermic. Okay, so stoichiometry involving the change in enthalpy, delta H. So you guys know that chemical reactions, it's not just reactants and products, right? There's also heat involved in chemical reactions. We saw that heat could be a product in a chemical reaction. It could also be a reactant, but we haven't seen much of that just yet. But bottom line is, when you're trying to find the change in enthalpy associated with a reaction, we call that delta H of a reaction, subscript Rxn for reaction. This is also called the enthalpy of reaction. And that all depends on the amount of material that's undergoing the reaction. Right? If we're trying to quantify how much heat was either absorbed or released in reaction, the question is, well, how much stuff are we reacting to begin with, right? Like we need to specify the amount, the quantity that we're reacting. Okay, so the amount matters. And remember how we did this when we've had a certain amount of something and we ran a reaction with that amount of a substance, and then we looked at the chemical equation that is associated with that substance, right? So for example, if I'm taking LP gas, propane, right, and I'm doing a combustion reaction where I'm reacting this with oxygen, I want to make CO2 and water. Here's my balanced equation. And notice there's another piece of information that's given to us that we didn't see before, but it's telling us what the change in enthalpy for this reaction is, how much heat was either produced or absorbed by the reaction. In this case, we have a negative delta H, right? Negative 2,044 kilojoules. The negative sign is telling you that it's exothermic, right? It released heat to the surroundings. So this chemical equation is telling you that for every 1 mole of this propane, C3H8 is propane, for every 1 mole of this and 5 moles of oxygen, for every single amount of those, imagine this is, we talked about chemical reactions like a recipe, right? So for every 1 of these and 5 of these, if you got 1 of these and 5 of these, and you combust them, you're going to release negative 2,044 kilojoules of heat. Okay, that's what this chemical equation is telling you. And let's say we started with a certain amount of propane. Let's just say we started with like 50 grams or something like that, right? So if I start with 50 grams, let me just write that out. 50 grams of C3H8. And the question is, how much heat is produced, or released, or generated when you react 50 grams of propane? Well, you could do stoichiometry to get there, right? First thing you do, everyone knows, is you convert grams to moles, right? So you multiply these two. And then you know that for every 1 mole of propane, I produced this amount of heat. And you can use that as a conversion factor, right? Like you can multiply this and have this as a bracket. And now you guys notice the grams cancel and the moles cancel. When you multiply these, you're left with kilojoules. Right? And you can do that math. It's going to be a certain amount of kilojoules of heat for 50 grams of propane that's combusted or burned. Okay? So bottom line is we can use stoichiometry to help us convert from an amount of a substance to the amount of heat that's either, expelled or absorbed by that system, by that chemical reaction. Okay? So why don't we practice a problem related to that? So here's a problem where it says you have an LP gas tank in a home barbecue. It contains 13.2 kilograms of propane, which is C3H8. We talked about that in the last slide. It says calculate the heat in kilojoules associated with the complete combustion of all the propane in the tank. Okay, so there's 13.2 kilograms of propane in the tank, right? So let's write that out. 13.2 kilograms of C3H8. Now they want the heat released, so we have to go from kilograms of C3H8 to kilojoules. Well, how do we do that? What's the plan? Well, if I know that for every 1 mole of propane, I release negative 2,044 kilojoules, right? I want to exploit that relationship, but the only way to get to moles of it is to go from kilograms to grams. And why do we have to go to grams? Because the only way to get to moles is use the molar mass, which is in grams, right? Molar mass is grams per mole, not kilograms per mole. So we got to go from kilograms to grams, and then grams to moles. And then from moles, we can go from moles to kilojoules. Okay? So let's set that up. Now we got a plan. Let's execute the plan. So we know that for every 1,000, oops, I put that in the wrong place. We want kilograms on the bottom, right? And grams on the top. So for every 1 kilogram, we have 1,000 grams. This is all C3H8. But then we know that for every 44.09 grams of C3H8, that's just the molar mass of C3H8. It's not given to you in the problem, but you can calculate it, the molar mass of propane. All right, so check this out. Kilograms cancel, grams cancel. We're left with moles right now, but we need energy. We need kilojoules. That's what they want. And we know that for every 1 mole of C3H8, we release 2,044 kilojoules of heat. Now the moles cancel. And we're left with that's the answer that we get. Okay, just multiply everything on the top, divide by everything on the bottom, and you should get that number. Oh, and I almost forgot, there should be a negative sign. Don't forget the negative sign, right? The negative's there. It's negative 6.12 10 to the 3. That's the amount of energy that was released for burning 13.2 kilograms of propane. Okay? So, guys, we just use stoichiometry. We're applying a concept we've learned before to a problem that is now involving energy. Okay. Practice problem for you. So this is going to be on a problem set. Notice what the question's asking. It's ammonia reacts with oxygen. Okay. And they gave you an equation, and they said calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. Okay, so try that one on your own, right? Notice the mole-to-mole ratio between all of these. Okay, there's 4 moles of ammonia, and you need 4 of these to release 906 kilojoules of energy. Okay, so exploit that stoichiometric relationship in your dimensional analysis setup, and you should be okay. Here's another practice question for you, right? What mass of butane in grams is necessary to produce this amount of heat? So you're kind of working backwards now. They told you how much heat is produced, and they're asking you, what mass of butane is necessary to produce that amount of heat? So just so you know, butane is C4H10. So this is butane, okay? And notice the stoichiometric ratios, right? For every 4 moles of butane, this is the amount of energy that is produced. Okay, so the question is, what mass of this is needed to to produce this amount of heat? They're also asking what mass of CO2 is produced. Okay, so same logic. Getting to the mass of butane, you can do the same thing with CO2. All right, and that's it for that one. Next video, we're going to talk about coffee cup calorimetry. Okay, that's also associated with change in enthalpy. So stay tuned for the next one.